Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we plant the seeds of weird and wonderful science directly into your imagination. I'm Ian Woolf. On this episode, you'll hear Dr Shelley Wickham talk about engineering tiny molecular train sets. But first up, here's news of Australia's security under attack. Surveillance data stolen. On the 8th of February 2019, Australian Prime Minister Scott Morrison announced that the Australian parliamentary computer system and the networks belonging to the Liberal, National and Labor political parties were breached by computer intruders that are sophisticated state actors, which is a technical term for spies from a foreign government. It was a large, well-coordinated attack that took a lot of resources. It's not known which nation has attacked Australia this way, and naturally, the Australian government is loath to make accusations without certainty, but everybody speculates. It's a federal election year in Australia. Could the attacking nation influence the Australian election? The computer break-in isn't thought to extend to all of the government department computer databases. The Australian government passed anti-encryption legislation last year following a loss of public trust with breaches of private census and health data, while promising that this time they could keep people's private data secure. The attackers appear to have used web shells, scripts that can be uploaded to a web server to allow the computers to be taken over and controlled from anywhere on the internet. Web shells also allow the attacker to gain control of computers that are on local area networks, but isolated from the internet. Quite separate to the Australian intelligence agencies and the police, Australian political parties surveil the entire voting population and keep extensive databases on every citizen. These databases of private information were on the computers that were broken into, along with emails and documents about how each party and politician planned to fight this year's national election. There would also have been security briefings and other government documents that should have been secure. The Liberal and National Party coalition uses the Parakelia Company's services to spy on Australia's citizens, in order to target and influence voters secretly using people's own data. Each Liberal National Coalition Member of Parliament and Senator pays the Parakelia Company for their surveillance database to help them get re-elected out of a taxpayer-funded office requisites entitlement, rather than their own money or money from the party. And the Parakelia Company gives a very large amount of money back to the Liberal National Party in return for them reporting to the company private information about the people in their electorate that they talk to. The legislation for these allowances states that they cannot be used for private or party purposes, yet the government's auditor office found nothing wrong with this arrangement. Nothing to see here. The Liberal and National parties use the i360 software from American billionaire Koch brothers with the Parakelia database to create models to test the effectiveness of thousands of political ads before using them. i360 also tracks your activities online, partnering with Facebook and Google Ads. This allows them to tailor their ads specifically for you. They can personalise the style and tone of the words in the ad. Even the looks and colours are set just for you. The Liberal National Party coalition won the South Australian election using i360. They will be using it in the 2019 federal election. The Australian Labor Party pays the Magenta Linus Company for their Campaign Central surveillance software. Magenta Linus does not give money to the Australian Labor Party, but it's still office requisites entitlement money that's being used for party business, even if it's not for commercial business. The political parties are able to spy on Australians because they agreed to give themselves a complete exemption from the Australian Privacy Act. And somehow this also applies to the private companies that spy on us for them. Perhaps there's a loophole here for a legal challenge? The result is that as well as all the surveillance data on every private citizen being kept on ASIO security intelligence computers, where it should be as secure as it gets, it's also kept on political parties' parliamentary computers, where it's been demonstrated to not be secure. It's also floating around on private company computers that may not be secure. In the USA and the UK, companies like Cambridge Analytica used this kind of personal information from Facebook to deliver individually tailored ads to persuade people who would have voted against Trump or against Brexit to choose not to vote at all. In Australia, voting is compulsory, with a $20 fine for those who don't vote. This means parties have to use a different strategy to persuade people to vote differently. In 2015 and 2016, there were high-profile attacks on the computers of the government's weather and statistics agencies. In 2011, senior Australian ministers also had their email systems breached by intruders identified as Chinese intelligence. Prime Minister Scott Morrison says that the Australian Cyber Security Centre worked with global antivirus companies to help them identify malicious activity. Consulting antivirus companies to protect national security and safeguard national elections? This is what Randall Munroe defined in his famous adult XKCD comic on electronic voting as doing it wrong. Relying on commercial antivirus software for national security is like defending yourself with a raincoat in a war zone. Recklessly inappropriate and bound to end in tears. To end up in this place, as the comic said, someone is clearly doing their job horribly wrong. An American researcher has filed 3 patents for weird technology on behalf of the US Navy. If any one of them turn out to work, they would change the world, and we will build statues to Salvatore Cesar Pais. I want them to be true, but it's really unlikely any of them work. Salvatore Cesar Pais has filed for 3 eye-popping patents. Piezoelectricity-induced room temperature superconductor in 2019, high-frequency gravitational wave generator in 2017, and craft using an inertial mass reduction device in 2016. So, the latest is room temperature superconductivity. Superconductors can be used to transmit electricity without loss over large distances, and also to make powerful low-powered magnets and for many other things. At present, they require very cold temperatures for the materials to change from weak conductors into superconductors. The cold makes them expensive and fragile. Researchers focused on new materials that become superconducting at higher and higher temperatures, but that are still quite cold, knitting liquid nitrogen instead of liquid helium. A room temperature superconductor would make power distribution much more efficient, saving billions of dollars, and would make powerful magnets cheap and easy for uses like magnetic levitation. The patent describes a device for generating superconductivity at room temperature using pulsing magnetic fields and a piezoelectric material, one that generates electricity when it's vibrated. It sounds like new physics, but not as out there on the edge as his patents for generating gravity waves or his patent for an anti-gravity spaceship motor that can travel faster than light. It seems strange that he developed the faster-than-light spaceship motor first, as I would have thought the more exotic technologies would build on the more ordinary ones. It's also odd that the PDF of the patent is an image, so you can't search it or highlight sections for copying. I'll go into the story of these weird technologies in greater detail next week. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Nanotechnology. Dr Shelley Wickham is a lecturer in chemistry and physics at the University of Sydney. She likes to take molecules and build them up like you would play with Lego. I began by asking her, how did she get into making things on a nanoscale into self-assembling structures?
That's a great question. So I started out studying nanostructures in biology. So you might know that some butterflies and some beetles get their wing color not from a pigment or a dye, but from a nanostructure that interacts with light. And when I was an undergrad, I was studying those, and I thought they were really cool, and I measured their optical properties, but then I wanted to make them. And it's really hard to make things on that scale. And so I looked up a professor in the UK who was the only person in the world at the time who could make them. And I said, I want to come and work with you. And he said, well, that project isn't currently working the way we'd like it to. Some of the equipment's not working. But you could come and work on this other stuff. It's a bit weird. It's to do with DNA self-assembly. And I thought that was the strangest thing I'd ever heard, but really exciting. And so it was kind of a sideways step that way, just because the particular instrument I was going to use for my PhD wasn't working. And so I went into this other project, which turned out to be much more fun to me.
That's amazing. And so self-assembling DNA. So we know DNA self-assembles in living things, but this is beyond that.
Yeah, so we take it, our DNA is all synthesized in machines, and it works just the same as in cells. So you have some set of nucleotides, so that's kind of the alphabet of DNA, and what happens in DNA is it binds to complementary sequences. So it's kind of like having special Velcro. You only sort of binds to the right type of Velcro, except instead of having just two sides of Velcro, we have many different ones. So you could mix 10 different Velcros in solution, and they'll all find the right pair. And so that's what we're doing, is designing them to pair up the way we want them to. And so then we just take our DNA sequences, mix them up just in water and maybe some salt, and then they assemble the way that we've programmed them to.
But you do more than just get things to join on like little Lego bricks.
Yeah.
They do much more.
They do. So once you've made something that's static, so it's a solid structure, you can use that as a kind of field or playground, if you like, and build molecular motors. So these are pieces of DNA that move around tracks, kind of like a little train. And you can make junctions and branches in the track and direct them. And so you have these molecules that can solve mazes, which is pretty fun.
So you can build little molecular DNA train sets.
Yeah.
That's astonishing.
It's really, really fun. It's really cool. And then the idea is that maybe as they go along the track, they pick up a molecule at each sort of station along the track. And so you could make custom molecules. You could also use them, so you might not know, you also have these types of molecular motors all around your body. They move things around your cells. They take sort of proteins to where they need to be in your synapses in your brain, and they make your muscles move. And maybe we could go in and make motors that walk around the body. That would be pretty cool. That's quite far away, but that's something that we'd like to do in the future.
But perhaps we can get them going on little rails first.
Exactly. We have to take little baby steps before we can have motors that can navigate your body. But ideally, we'd like to have a motor that could drive a nanoparticle around your body to help diagnose disease or maybe even treat the disease once it finds it.
So you could use the little micromotors that little bacteria and things use.
Right now, we're not using the ones from bacteria. It's more like we look at what bacteria does and how it swims around, and we try and copy it using our own materials. But you're right, you could take those proteins as well and integrate it and have a hybrid system that's part protein from a biological source and part DNA from more like a chemical source.
So at the moment, you can have these little motors going around the little model railway track, picking things up and assembling them almost like a little factory.
Exactly, like an assembly line. Yeah.
So what sort of things can you make?
Well, right now, nothing very complicated. And that's because we spent a lot of time designing the motors, and now we can explore what can the motors do. And that's something that we're working on.
Do you have video of these little nano things moving around?
Yes, actually, I managed to do that in my PhD. It was pretty exciting. We use a technique called atomic force microscopy, which is a way of seeing on a 2D surface individual molecules, that's what really got me excited about this field. The first time I saw a picture of a molecule, I was like, wow, that's amazing. You can see it, and it really looks like it's supposed to look. When I saw those diagrams in textbooks, I just thought, oh, I'm not entirely convinced by this. But now when you see it, you really believe it. And so you can take a movie of them. And so I was really lucky, and I got to go to this lab in Japan where they had a high-speed, they're called AFM, and there we could actually watch this little motor take individual steps. And if you think of it, the size of the steps was 6 nanometers. So that's like it would take, if your hair is about 60,000 nanometers, it would take so many steps to even cover one hair. And we saw it taking 5 or 6 steps, which is pretty awesome.
And what's the energy source for the motors?
So you can power them lots of different ways. So people have done using light, so you can use photoactivation. People have done some really cool ones lately with electric and magnetic fields, and that's great because you can control them outside. And that's an idea, like if you have it in the body, you'd like to control it outside the body. In that case, we're using enzymes. So enzymes would cleave the backbone of the DNA, and that breaking that chemical bond releases energy, and that's what's pushing the motor forwards.
And would you be able to get them to make more of themselves?
That's a great question. No, with our current designs, like we're synthesizing all the DNA ourselves. The way that a cell is able to replicate itself and make more motors, that's very, very far beyond what we're able to do. That would be a very, very far away goal.
And the synthesis of these little nano parts, is that something that once you've done all the hard work of understanding how to do it, that other labs with these sort of synthesizers could do?
Exactly. And that's another thing that really attracted me to this field is it's a lot of very clever design, and then the experiments are relatively straightforward. So once you publish a paper, you publish all the DNA sequences you need, and then anyone can buy them, and lots of labs, and you don't need a particularly sophisticated lab to do some of these experiments. And so what that means is the whole field moves really quickly because, say, for example, I use one technique called DNA origami, where you fold up large pieces of DNA into really intricate shapes, just like you would fold up a piece of paper. And that paper was published just when I started my PhD, and I'd never done really any biochemistry. I was a physics student, and I'd never used an AFM, so that atomic force microscope, before. And within the first month of my PhD, I had a picture of a molecule in the shape of a square, this rectangle with really specific dimensions that was exactly like the one in the paper. And for people who work in science, sometimes it's really hard, even if you know exactly how to do it, to reproduce something. But this field is really reproducible, and that makes it move really quickly, and it's very exciting and very collaborative as well.
But do you have to go to another country with an atomic force microscope to be able to see the results of what you've done?
Not necessarily. So here in Australia, we have lots of AFMs, and that high-speed AFM, I was lucky at the time to go to Japan because that was a really new type of instrument, and they had like the prototype instrument there. But now those techniques are more readily available. So we can do AFM here at Sydney Uni. We can do electron microscopy of them as well. So there's lots of ways to see them.
So if somebody was starting their academic career or even going to uni for the first time, what would they study to get into your field now?
That's a great question, and one I really like, because another thing I really like about what we get to do is we work with people from all over. So we had a meeting today, and there were biochemists, chemists, physicists, mathematicians, people from engineering, people from biological sciences, people from medical sciences, people coming from more of a clinical background like nursing or being a doctor. And so it's very collaborative, and I think you can approach it from whichever subjects you're most interested in. So if you have a particular passion for physics, you can bring that physics knowledge and that physics way of looking at problems to it, which is what I did. At the same time, you can work with people who have totally different backgrounds to you. You might be experts in cell biology or molecular motors. So really whatever you're passionate about.
And do you think this is the sort of thing that some of these citizen biologists, biohacking labs would be able to reproduce some of what you've done?
Yeah, I think so. And I think there's some Instructables pages on making DNA origami and things like that. It's very accessible, and a lot of the techniques are very basic. A lot of the beauty of it comes from the elegant design. And a lot of those design tools are also open source. And so there's a lot of software out in the community that people are very happy to share and quite intuitive to use, because we make everything abstract. Rather than thinking about the molecules, we come up with sort of very simplified ways of representing them. And so they're quite accessible to lots of people.
And you mentioned that you want to get them to walk to be able to go around in the body.
Yeah.
What do you think are the earliest applications that might come out of the work?
So I think one that people are already looking at, not particularly us, but other groups, is can you have targeted drug delivery to cancer? So the problem is you get all these side effects from chemotherapy, they're really bad, and they limit how much you can of the drug you can give to people. But what if that drug knew how to go exactly only to the tumor and not affect any other tissues? And so that sort of targeting is a field that DNA nanotechnology can do. And there's some really lovely papers that have come out showing that that could be a possible application. So I think that would be the first one to come through.
And what do you see as the more advanced things that will come?
That's a really hard thing to predict, because we can make any shape. And so what would it be? I think some of the really nice things that could happen is using them as kind of nanoscale tools to understand biological systems, because there's lots of proteins in your body, especially the very complex ones like motors, where we don't really know how they work. And that means that when they break down, so maybe there's a problem with one of these motor proteins that's in your brain and it leads to a neurodegenerative disorder, how do we know why it's broken, and then how do we fix it? And so these nanostructures can be tools like little sort of pliers or springs or tweezers to hold these proteins down and really understand how they work so that we can solve those problems. So I think those kind of more interesting abstract ideas of making tools to understand biology is like a really big picture problem that it could solve.
Would those tools also be able to apply to chemistry?
Yes, I think they could be. The challenge there is, are the conditions compatible? Because lots of chemistry doesn't happen in water, whereas our DNA, like our biology, is all based on water. And if somebody could solve that problem, then I think definitely it could. Right now we're restricted to only the chemical reactions that happen in water, which for chemists is not really the interesting stuff.
Well, Shelley, thank you very much.
Thank you so much.
That was nanotechnologist Dr. Shelley Wickham talking about building molecular motors for tiny train sets and DNA origami at the University of Sydney.
I've been around a lot and talked with some of these research men, and they won't make predictions because they deal only in facts. But they're on their way to new ideas, new things that will astonish us when they are announced. For instance, already industry is making airplane propellers with sour milk as an ingredient, roads from cotton, and artificial leather from the same material. The time may come when the American farmer will grow a crop of automobile engines or rocking chairs, gasoline from sea sand, rubies from peach pits, artificial wool from cheese, but not with the holes. So maybe the moon is made of green cheese, and even if it isn't, the explorers of the research laboratories could probably find a way to do it. One thing is certain. It is these research activities that have brought us this far and will continue to create further progress for us. And the industrial scientists and engineers are the pioneers of present-day America, the creators of progress, of new industries and new jobs. It's a bewildering future, all right.
And that's all from us this week on Diffusion. Would you like to hear your voice on radio? Record a voice memo on your phone or use the voicemail tab on the website. Ask me a question I can answer on the show. We need more people contributing stories to Diffusion. Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please do send me an email so I know someone's listening. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. Sound and fact-checking by Charles Willock. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including 2RBM in the Blue Mountains of New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, 2XXFM in Canberra, and my local station, 2RDJ in Burwood, New South Wales. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 950 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio. Make a donation through paypal.me/Ian Woolf, or listen to Diffusion on your phone or tablet through the Radio Public app. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.